Hey everyone, hope you're doing well. So, like I said in the last video, I've implemented type checking, and I'm actually pretty far with the self-hosted Alexa. So, um, we already tokenize like most of the source code, but there's still a major bug that I want to fix before I can make a video about it. So for today, I thought it would be fun to prove that ELO is Turing complete. I mentioned it in the description of an earlier video, but I've never really explained it. So Turing complete programming language means that it's able to compute anything that any other Turing complete programming language could compute. So it's always a milestone while writing a toy programming language, even if it's quite easy to achieve. Now, the most common way to prove your language is Turing complete is to implement another Turing complete system in it. And there are two Turing complete systems which are very easy to implement. The first one is Rule 110. I'll show you. I'll show you. Hey, Poos. Let me see. Rule 110. So that looks like this. It's a cellular automaton, and it's discovered by Stephen Wolfram. You might know him from his awesome application website, Wolfram Alpha. Well, yeah, Rule 110 looks like this, and someone has actually proved that these patterns could be used to calculate anything that a Turing-complete computer could. So, yeah, Rule 110 is Turing-complete. So we could implement that. But there's another programming language which I really love, and I've written a lot of things in it. It's called Brainfuck, and it's probably the most famous, so-called esoteric programming languages. And it's easy to see how it's Turing complete because it's actually quite similar to a Turing machine. So now, if you're not familiar with any of these things, please look it up because it's all very interesting. Okay, now it's called Brainfuck because writing anything substantial in Brainfuck is actually relatively hard. But Rule 110 is so easy to implement that a couple of years ago I've implemented it in Brainfuck. Let's see, this one. So this is Rule 110 in Brainfuck. This is the actual Brainfuck program. And this is its output. So you see the patterns here. And this is a Brainfuck interpreter in C, which executes the Rule 110 program. So I'll put a link in the description to this repository. But I thought, why not create a Brainfuck interpreter in ELO, which executes this program, Rule 110 program, and yeah, sounds like a cool way to prove it's Turing complete with in more than one way. So yeah, let's do that. Let's make a file, brainfuck.elo. Okay, let's first quickly summarize how Brainfuck works. So you have a memory, which is an array of values. Let's say it's this, and you've got a pointer, and you've got 8 instructions. And you've got a plus and minus, which increment and decrement the values. You've got greater than and less than, or right and left, which move the pointer to the left and the right. And you've got, for input and output, you've got comma for input. So the comma waits for user input. Let's say we pressed enter, so that's a new line, so that's 10, and then 10 is filled in the current cell, and you've got a dot, a period, to output it. So output whatever the value is in the cell, converted to its ASCII value. So, and then the last two are brackets, opening and closing straight brackets. They are used for branching conditions. So, for example, if I would write a program that does this, so it's a plus, then we put 1 there, we increment it to 1, then we have an opening bracket, and let's say it's this. So this is an example program. When you encounter an opening bracket, you skip this code. You skip this code if it's if the current value is 0, and you enter it if it's not 0. So right now it's not 0, so you enter this. Then you take whatever the user inputs. So let's say it's 10 for new line. And then you go to the period, and it outputs whatever the user inputs. So whatever the user has input here, it outputs it, and it continues until the user input is 0. In other words, until end of file. So this is actually the cat command. It, well, sort of, not really, of course, but it repeats what the user inputs. So yeah, that's a quick summary of the language. So let's implement it. We'll need the standard library. Let's create a main function. We don't care about its inputs, and yeah, we'll return an integer. Okay, so we'll need some memory. Let's see. Let's say mem. So this is an array of characters. Then we'll need a memory pointer, which is a pointer, obviously. And then we'll need a program pointer. We need to know where in the program we are. So that's also a pointer. Okay. So the first thing we want to do is we want to make sure this memory pointer points at the first cell of the memory. So let's do that. So we take the memory pointer, the pointer to memory, put it on the stack, and put the pointer to the memory pointer on the stack, and then we set the pointer. So now memory pointer contains a pointer to memory. Okay, so that's initialized, and let's start with let's say we have a program here. Let's create the cat program we've discussed earlier. Okay, something like this, and then right now we have a pointer to the program on the stack. So while this pointer dereference, while the character it points at let me check. I think I need an updated syntax. Okay, so we take the character we point at in the program, and we check if it's 0. And while it's not 0, so we're not at the end of the program, we want to check, okay, is the value, for example, equal to plus, like this. And we could do the same for the other instructions. Plus minus to the right and to the left. Let's see, we want output and or input and output. And we have the loops branching. Okay. So that will be our structure, and afterwards we'll increment the pointer to the program so we get to the next character of the program. So something like this. Okay. Let's first start with an easier one. So we just return one single character. Okay. Maybe, yeah. Let's start with this. So I think I want to write a different function, get character. We don't have an input argument, but we return a character. Okay. Let's think. I think we'll need a read. Yeah. Okay. So let us get the standard library, and I've created a wrapper for the read syscall. So reads from a file descriptor and returns the number of bytes read or 0 if end of file. So the file descriptor we know, that's standard in. Buffer we have to create, and count will be 1. We want to have one single character. So, okay, we first need to allocate 1 byte of memory, and we have to keep track. Let's see, let's start with this. So we duplicate the pointer to this memory block of one byte. We add the standard in and swap it. So right now it's the file descriptor is first and the buffer is second. And then we can add count. We execute read. And this will return 0 if it's end of file, and otherwise the number of bytes read. Yeah. We actually need to wait for the user to actually input a character. So we need to create I think, a while loop. So let's say this is characters read, while this is 0. Yeah. Well, this is 0. We want to do this. We can drop the characters used here, characters read, I'm sorry. And then read will return the number of characters read. If there's no user input yet, it's 0. So it will wait. It will be inside this loop until there's something read, and then it will continue. So yeah, we need to drop whatever read returned. And let's see, we want to dereference the buffer pointer, but we also we need to free the file descriptor. So let's see, we want to duplicate the buffer, we want to dereference it, we want to swap it and free it. So we free the allocated byte here. So this should get us a character. Okay, so here, let's see, I think we need to take the memory pointer. So get character and put it in where the memory pointer contains the pointer to wherever in the memory we are. So this will have a pointer, this will have a character, so we can do set C. And then the output, we have to convert the character into a string. So let's see, string will need 2 bytes instead of 1. First byte will be the character, second byte will be 0. So we have a valid string. Okay, so we have a buffer here. Want to duplicate that buffer because we want to keep the value, the pointer to the buffer later, to later free it. Okay, we want to duplicate. We want to get the memory pointer value and get the character it points to. Then we need to swap and set it like this. Okay. So now it's set. And we want to take the second. So dupe to get the first pointer to the first byte. We want to look at the second byte and put a 0 character there. Again, swap and set. And then we want to print the buffer, and then we can free it. So I think when we execute this, we will first take input and then print it. So let's try to run it. Brainfuck, let's test an ASM. Okay, test, and we'll need input. So if I input A, it returns A. Other way to do that is echo foo into test. Awesome, so our program works. Okay, that's cool. Okay, well, these should be easy to implement. So let's start with these two. So we move to the right, so we increment the memory pointer. So we take the memory pointer, the value of the memory pointer, not where it points at, but its value. We increment it, and then we put it in MP into the memory pointer buffer. And this is the same, but it's decrementing. These are similar, but instead of using the pointer, incrementing and decrementing the pointer, we actually want to, let's think, so we want to deref C, so we have the character, which we point at. I think we need to cast to integer for this to work. Might want to be able to change that. Okay, so, and then we need to cast it back to cast C. And then we'll need a pointer to MP derf P. So I think I will duplicate here. And I'll duplicate there and then swap here. So we set. So okay, let's break down what happens. After this, we have a memory pointer. We get the pointer to the memory pointer and double it. So we've got this. Then we dereference it. So we get the character. We convert it to an integer. We add 1 and put it back, convert it back to a character. I'm sorry. Then we swap it. We swap it and we set it. So that's the way it works. So let's do something like this, and instead of incrementing, we need to decrement. Okay, so now we can make something else. Like, what if we take input, we go to the next cell, we take input, Then we output whatever that cell is, and then we go to the left and we output. So we should input 2 characters and output them in reverse order. So let's build it. Some tests. What if I say AB? We get BA. Awesome. Cool. So, okay, these seem to work. Then we have 2 left, and these are a bit more interesting. I think for this I will now can have the cat program of earlier. So let's do this. Then we do this. So whenever we encounter a opening bracket, if the value is non-zero, then it's a no up. We just want to continue, go to the next character. But if it's 0, we want to skip this. So what if you have like brackets within brackets? So you need to keep track of the number of brackets. So let's add a counter. Let me think. Just a second. Yeah, we need to check memory pointer and dereference the character. And then we need to know if it's equal to 0. If the character is equal to 0, then we need to skip. So we have a counter, the bracket counter, and while this value is unequal to 0, let's think. We want to swap, so we get, okay, I'll explain what the stack does. So right here we have the program pointer, so the program pointer and the counter. That's what we have here. So we want to swap them because we want to increment the program pointer. So just say that it's changed like this. Okay. Then we want to check if this program pointer points at a opening bracket. If it does, we need to swap again because we want to increment the counter. We'll do the same, but the other way around for closing brackets. So we decrement, and then we swap again to get back to this state where the counter is on top of the stack. So, okay. I think this should work. There's one thing we need to drop. Is this the good indenting? Yeah. So we need to drop the counter. We're not going to use the counter. Okay. So yeah, this should skip the code, and when we're at a closing bracket. Let's see. So when we're at a closing bracket, let's say there's more code here. When we're at a closing bracket, if the value is 0, we want to skip. It's a no up. But if the value is non-zero, for example 1 or whatever, we need to go back to the matching bracket. So it's almost the same, but the other way around. So instead of, let's see here. Instead of going to the right, we want to go to the left. And instead of, we want to change these two around. Yeah. Now we're counting the other way around. So maybe this will work. So what do we expect it to do? We expect to echo everything we enter. So the standard in should be put as a standard out. So let's see. We compile it. This. Okay. So ABC. Okay, something went wrong. So I think, yeah, it just takes the first. Oh, I know what went wrong. Yeah. When we have an opening bracket, we want to skip when the value is 0. When we have a closing bracket, we want to skip, so go back when the value is not 0. So it's the other way around. So this needs to be like this. So I think that was the bug. I first need to do this. Yeah. Like that. And we echo foo into test. We get foo. Awesome. So that's really cool. Now we have the ultimate test. Okay, cool. The ultimate test. Let's take this program. I currently don't have a way to handle multi-line strings. But what we're gonna do is we're just gonna make different strings like this. Let's see, so I want to append this to make it a string. And then I want, let's remove this. So I want to concatenate these. So what I will do is this. Concat takes two strings and puts them together. That's what it does. The only thing it does. So this will result in one big string. So let's check it out. Let's try if it works. That would be cool. Okay, so how the Brainfuck program works, it takes zeros and ones. Let's just start with the easiest example, which we know and love. Yeah, it works. Look at that. Oh, that's awesome. So you can have any initial state. So let's say ones and zeros here. And it just computes the next state like that. Awesome. Okay. So that's our rule 110 in Brainfuck in Elo. That's cool. So this is how we know Elo is Turing complete. Yeah. Okay, cool. Okay, so what's next? Yeah, like I said earlier, I will fix that bug, and then we'll discuss how type checking is handled, and probably the tokenizer, the Lexer. So we're on our way to have a self-hosted compiler already, which is really awesome. So yeah, I hope you enjoyed it, and I'll see you next time. Bye bye.